Welcome to the second lecture on Ethereum. Yesterday we were talking about the core of Ethereum, layer 1. So today we are going to talk about smart contracts on Ethereum. The concept of smart contracts was first proposed around 1994 by Nick Szabo, who was a legal scholar and cryptographer. So his idea was essentially the same as what we are using smart contracts for today, and that was to replace, replace the human intermediaries with something automated. And also he envisioned that legal contracts on paper could be replaced by some mechanisms which would be automated. So compared to a human intermediary, it's cheaper to involve a smart contract, so you don't need to pay fees to the intermediary. The contract is an open and transparent program that fulfills the contract and does nothing else. For example, doesn't peek into your data. And the contract can be made highly resilient to attacks, but at least you know the level of security provided by the contract. Compared to similar technologies that were used in the context of distributed databases, we could say that contracts are rule-based rather than data-based. The collection of rules is transparent and reusable across different contracts. A contract is actually like an active object. A contract may decide to take certain steps. It may initiate and play an active role in the communication. It may integrate and fuse data from multiple sources. So it's more like an active entity compared to a database, which is just storage of data. However, around 1994, there was no blockchain. So at this point, the idea of smart contracts was proposed as a concept independently of the ledger. It was not until 2013 that Ethereum combined the two concepts together. So the contract layer in different systems has different features. So we have not seen Hyperledger yet, but we can already compare Bitcoin and Ethereum. So on Bitcoin we have some simple scripts. In Ethereum we have Turing complete smart contracts. The programming language in Bitcoin is a script programming language. In Ethereum there are actually many languages, like as many as 10 different languages are used for writing smart contracts in Ethereum, but Solidity is the most popular one. And today we'll briefly go over Solidity. So the contracts are executed on nodes, are not executed on lightweight nodes. And the contracts in Ethereum are translated into Ethereum bytecode and executed on Ethereum virtual machine, which supports the Ethereum bytecode. So contracts contain executable bytecode, and they also have internal storage. How are contracts created and registered in Ethereum? There is a special transaction which registers a contract, and that transaction provides the code of the contract and also puts some budget into the contract. And contract consists, it's like event-based programming. Contract consists of many functions, and those functions can be triggered at different times. So there are different types of functions, as we will see today. Execution time is limited by gas, as mentioned. A contract can be so what's the trigger? Well, there is constructor function for a contract, but most of the functions are invoked by RPC, remote procedure call. So they are triggered by other transactions or by other contracts. Can also be triggered by a timeout, for example. So what you see here is an example, right? Where the contract would be stored in the chain-based database. So, there, like in block 3, there is a transaction create transaction. And the transaction would have own. Here what you can see is a bit more detailed representation. The code of the contract is secured by the hash of the code, which is stored in the database. So for a contract, you can see the balance, the code hash, and the reference to the root hash of the partition of the contract. And the user, while some other accounts can be contract accounts. There are two types of accounts in Ethereum. So now we can take a brief look at Solidity example. And the example taken from proof of existence contract. Of address. Okay. Version. So this is definition of a type listened to by any client. It automatically generates getters and setters. Here there is a modifier, is a special kind of function in Solidity. What does it do? Prepends to any, and it's like a condition. You can see the modifier starts with fire. So if the condition doesn't hold, then the execution of the function is aborted. And the same modifier can be included into multiple functions. This is a constructor instance, which is executed when the contract is created, so it's typical for object-oriented languages. And now this is the core function of the contract, which allows the owner to confirm a document ID with a given content. Here we create the proof created event. It was defined in the previous, and we publish this event to the blockchain. And new function, keyword, very important keyword, because it means it doesn't modify the state. If it doesn't modify the state, and its execution doesn't cost any gas. Only execution of functions which modify the state requires some gas. So these are some of the features of Solidity. Now, what do we need to do with contracts? We need to, after we create a contract, we need to compile the interface to the contract. So we configure the interface. Then we deploy the new contract using a new contract transaction. So transactions, and then so this is how we create a new transaction. Usually you don't need to write all this code yourself, because IDEs such as Truffle and Remix automatically compile, deploy, and test contracts. However, using smart contracts doesn't come without challenges. It's a replicated execution. So the same function is executed in many different places. So what are the challenges related to that? The first challenge is non-determinism. What happens if the function is non-deterministic? In that case, it may return different results on each copy or on each node executing the function. So that would be it then. If it returns different results, how can we verify the correctness? We are keeping receipts from executing the function. So if each time the function is given different result, what's the point of a receipt? We cannot verify that it executed correctly. The next problem is side effects, right? Imagine that the function does some non-idempotent operation. So, for example, it could be calling some external service, and then suddenly the service would be called 100 different times if there are 100 nodes on the blockchain. Such challenges related to non-deterministic are resolved by interacting with the oracles. What is an oracle? Oracle is an entity external to the blockchain with which blockchain interacts. Oracle usually does some sensing on behalf of the smart contract, and it would know the answer. So it works both directions. An oracle would provide information to the smart contract, and an oracle would also consolidate the requests from different copies of the smart contract. It's called an oracle because it would know the answer. And that definitely helps with invoking external services, because then the oracle would invoke external services only once. That's not all. Next, upgrading and fixing a contract. I mean, how do you usually upgrade the software? You upgrade the software so suppose you fix the bug. Now you have a new version, local version of the software, but the old version is still running. So you store the state. The old version of the software would store the state. Then you would usually bring down the old version for a brief period of time, and then you launch the new version. It's not as simple with smart contracts. What's the problem? The problem is that the smart contract may store some data on the blockchain. And when you launch the new contract, how would the new contract get access to the data stored by the old contract? So there is a need for some sophisticated control schemes. So upgrading contracts is actually a painful operation. you need to be very careful, especially because contracts are prone to bugs. And indeed, there are bugs which are specific to smart contracts, so which you would not see in other types of programs. And today we are going to see some of those bugs. I mean, one direct implication is that you can directly lose money due to bugs. So writing smart contracts may require some economic thinking perspective. You need to consider incentives of the participants. So now we are going to see a few buggy contracts. This contract implements a rock, scissors, paper game. So we have two players, and each player is supposed to, each player joining the game deposits some funds, right? And also provides the value. And finally, when all the players join the game, the contract would check the values and would declare the winner and transfer the funds to the winning participant. Okay, so specifically how it's implemented. There is the init function, which initializes the number of players to 0, and the most interesting function is player input. If number of players is smaller than 2, and the value in the message to 1,000, so 1,000, the two players game with a 1,000 weight price. So each player deposits 1,000, and then the winning player would collect all the winnings. Okay? So if the number of players is smaller than 2 and the value in the message is equal to 1,000, then we proceed with execution. Otherwise, we return -1, means that that's not the correct interface. So we are not proceeding with the game. Okay, so we increase the reward with the value of the message. And we memorize the address of the player, and we also memorize the choice of the player, and we increase the number of players. And there is also one final function which is not shown here, which checks the results, the value submitted by all players, declares the winner, and sends the fund back. So that's the implementation. Now it's very simple program, right? Turns out that it already has up to 5 different bugs. So what's the first bug? What happens if a third player joins the system when 2 players have already joined? Here, if the number of players is not smaller than 2, then return. Instead, we are supposed to transfer the back to the player who could not join the game. So that's missing here. And the same problem happens if the bet is not equal 1,000 weight. If by mistake the player sends a different amount, the player would simply lose the amount because the amount is not transferred back. Okay, that's the first pitfall. The second pitfall, the value, the choice here is sent in plain text. Why is it a problem? It can be easily exploited. What happens is that a player may wait until someone else places the bid. Then the player may check the state and would see the bid. I mean, the whole point of rock, scissors, paper game is that everyone is supposed to provide the value simultaneously. If a player is able to see the previously submitted values, then it gives an unfair advantage to the player. So that's a problem with sending the values in plain text. Okay, so what can we do about it? We do the same technique which is used in zero coin, in zero cash. We submit a commitment. We do not submit a plain text value. We hide the plain text, the value submitted is a secret. Instead, we submit, each player would submit a commitment to the value. And only after all values are submitted, only then the contract would request the players to submit the actual value, and then it would be possible to verify that the values submitted indeed correspond to the commitment. Problem number 3. What happens if, in some cases, the node, the participant may have an incentive to abandon the execution? How so? For example, a player may wait until the other player looks at the result, and then the player can guess that the other player is winning, and in this case the player would not be continuing the execution. Why is that? What would the player gain by not continuing the execution? The player would lose the bet anyway. Well, what would the player gain is that the player would not need to pay the gas on executing transactions. So pitfall number 4, there are Ethereum-specific constraints, such as the limit on the size of the call stack. If a function is, if the call stack becomes too long, the execution would abort. And it turns out that can also be exploited, especially like if the attacker can control the size of the stack. You abort execution at the right moment, and by doing that, you can avoid paying, for example. You won't transfer in the funds. And the 5th pitfall we are going to consider. What happens if we set the reward higher than the block creation reward? If we set the reward in a game higher than the block creation reward, and the miner is participating in the game, then it becomes more important for the miner to get the game reward than to produce a block. So imagine that the miner mines a block, and then the miner successfully mines the block, and at this point the miner would be able to see that the miner would lose the rock, scissors, paper game. The miner may think twice, why would I publish this block? Maybe I should wait until someone else would produce a block, and then I get a second chance of winning the game. So that's yet another problematic scenario, and all of this just for a very simple program, very simple game, right? So now you can think of what happens with real-scale industrial applications. And by the way, this example is taken from a paper called Step by Step Towards Creating a Safe Smart Contract, Lessons and Insights from a Cryptocurrency Lab. So it's how did they identify all those problems? They actually announced, like they define the game, and they invited students and programming engineers to come to the lab, and then they asked them to implement the contract, and they gave them even sufficient time. And then they collected they also had presentations, they collected the results, and they analyzed the submitted contracts and saw all the problems which were popping up in different implementations. So it was an insightful exercise. Now here we can see a very famous example of the DAO attack. So it was an attack on Ethereum where a particular organization raised around $150 million before some point in June 2016. And an attacker managed to steal around $60 million from that DAO using the bug which I'm going to explain. So it was a major theft. And then, as usual, there was a discussion what to do with the theft, and there was a hard fork of the blockchain that nullified the effect of the transactions. And of course, some participants were very unhappy because it's a hard fork. Okay, so how did it work? Okay, this is the gist of the DAO. Contract simple DAO, and you can donate funds to DAO, in which case, so manage an account from different participants, right? So if you donate to DAO, then the account would get increased by the value. Okay. And there is a question which just returns the current value of the credit. And then there is a withdraw function. What does the withdraw function do? It checks the current balance, and if the current balance is not smaller than the amount, then it would invoke a callback on the sender, providing the amount, and then it would basically the callback would like notify the sender, yes, the withdrawal is going well, and then the credit would be subtracted from the credit. So it doesn't look suspicious at all, right? You check the balance first, and if there is enough balance, then you notify the sender, and then you subtract the value from the balance. Turns out the critical difficulty here, and it's exploited by the following contract. So what does the contract do? Here is the constructor. So in constructor, just memorize the sender. And then the critical function is the one which receives the callback. What does it do? It calls withdraw in recursively. So what happens here is that the withdraw is called recursively before, and that's a critical point, before the amount is subtracted from the credit. And then it would continue to withdraw the funds in an infinite. Well, not infinite, because the size of the whole stack is limited. But it's limited by a very large number. And that's the number of times the attacker was able to withdraw the funds. without getting the balance reduced. So it's a very, with quite devastating results. Here's another example of security problems in smart contracts. Here's a contract which implements the Ponzi scheme, but it doesn't matter what exactly it implements. And an adversary managed to steal some Ether from the contract because of the bug in the contract. So initially, the contract was called Dynamic Pyramid. But during the development of the contract, the name was changed from Dynamic Pyramid into a different name. However, the creator of the contract forgot to change the name of the constructor. So, okay, so now of course the constructor doesn't run. That's one problem. But now a bigger problem is that everyone else can invoke Dynamic Pyramid. What does Dynamic Pyramid do? It says the order of the funds to be the center of the message. So it was the intended functionality of the constructor, because the constructor is only called once in the beginning, with the center being the creator of the contract. But now everyone can call this function and set herself or himself as the owner of the contract. So please note that we've seen many bugs today. Please note that none of those bugs arise in an environment other than smart contracts. They are specific to smart contracts. They cannot arise in normal programs. So this is why people claim that developing smart contracts is more difficult than developing the normal programs. Okay, still on that topic, I would like to say that, so other tools that test smart contracts for potential vulnerabilities? The answer is yes, such tools are being developed and being improved. However, there are many languages for smart contracts, right? And each language needs a different set of tools. So it's a long process. And the tools today are getting better. But still, bugs can be easily introduced. Now, another analysis I would like to present is some statistics. On different distributions of smart contracts. So in this analysis, the authors looked at all smart contracts deployed on Ethereum for a certain period of time, and they tried to analyze the distribution of transactions, like how many transactions are due to each contract. And they also tried to analyze the balance of contract. What balance, what's the size of the balance in proportion to the size of the balance of the other contracts. So in total, there were about 10,000 contracts, and the total amount of funds owned by the contracts were, I believe, about $50 million. I don't remember the exact amount. But the interesting thing is the distribution. So they observed that very small fraction of the contracts is owning almost all of the balance. And also a very small fraction of the contracts is responsible for almost all of the transactions. So it's like a power law distribution, right? So what you see here on the x-axis is the amount of contracts, right? So this is a cumulative CDF. And this is the probability. What you see on the y-axis is the probability of a contract to exceed the value. So it turns out that that distributions of smart contracts are heavily skewed in terms of both the balance and the number of transactions. They also looked at the number of code lines per contract. So you can also, here you can see also typical, I believe it's an exponential distribution, right? So, so almost, or it could be Pareto as well, almost all, most of the very few contracts, number of lines exceeding 1,000. And essentially there is only a contract with the number of lines exceeding 2,000. So right now, most of the deployed programs, deployed contracts are very short. And this is both because of the complexity of writing the contract, but also because of the gas limitations. Because running the contract execution means that one needs to spend a lot of gas. Therefore, in most cases, long contracts are not beneficial. It's interesting that the bytecode length is a bit different from the number of lines. It doesn't look like the exact distribution, though of course the two are similar. So the originally written contract and the compiled contract have slightly different lengths proportionally. And this is the end of the lecture. I would like to thank you, and I would welcome